The typical accuracy of digital multimeters is around plus or minus 0.5% to plus or minus 2%. In the scenario described, this means the first meter could have been reading up to 479 volts times 1.2, which equals 467 volts, and the second meter could have been reading as low as 479 volts times 0.98, which equals 468 volts. Several factors can affect voltage drop calculations. Firstly, conductor length. The calculation may have overestimated voltage drop. If the conductor length was slightly shorter than 1050 feet, the voltage drop would be lower. Secondly, conductor material. Number 2 XHHW has lower resistance than some other conductors, such as aluminum. Thirdly, ambient temperature. If the installation was done in cold weather, the conductors would have had lower resistance than at higher temperatures. Adding load will increase current flowing through the conductors, which will increase voltage drop. The amount of voltage drop depends on the load and the impedance of the conductors. Extreme hot summer temperatures can increase conductor resistance and therefore voltage drop. This could become an issue if the load is high and the conductors are not sized appropriately. Added resistance to the transformer will reduce the voltage supply to the comm room. Long term, this could become problematic if the voltage drop is significant and affects the operation of equipment in the comm room. Let's delve deeper into voltage drop calculations and the various factors influencing them. Voltage drop is the decrease of electrical potential along the path of a circuit. It's an inevitable phenomenon in electrical systems due to the resistance of the conductors. Managing voltage drop is crucial to ensure that electrical equipment receives voltage within its operational tolerances. If the voltage is too low, equipment may not function correctly, or its lifespan may be reduced. There are several key factors to consider when calculating and addressing voltage drop. Firstly, conductor length. The length of the conductor is directly proportional to voltage drop. The longer the conductor, the greater the resistance and, consequently, the higher the voltage drop. In the scenario provided, the length from the distribution point to the disconnect is 1050 feet. If the actual length is less, the voltage drop will be less than calculated. It's essential to measure the conductor length accurately to refine voltage drop calculations. Secondly, conductor material and size. The material and size of the conductor significantly affect its resistance. Copper and aluminum are the most common conductor materials, with copper having lower resistance than aluminum for the same size conductor. The size of the conductor, expressed in terms of its cross-sectional area e.g., American wire gauge or AWG, also affects resistance. Larger conductors have lower resistance. In this case, number 2 XHHW is used. XHHW is a type of cross-linked polyethylene insulated wire that is commonly used in power distribution systems. Number 2 AWG has a specific resistance per unit length, which can be found in standard electrical tables. Using a material with low resistance or a larger conductor size can reduce voltage drop. Thirdly, current. The amount of current flowing through the conductor is directly proportional to voltage drop. Higher current leads to higher voltage drop. The load connected to the circuit determines the current. In this scenario, a 70 amps 3-pole breaker is feeding a 45 kilovolt amps transformer. The actual current drawn will depend on the load connected to the transformer. Accurately estimating the load is critical for voltage drop calculations. Fourthly, temperature. The temperature of the conductor affects its resistance. As temperature increases, the resistance of the conductor also increases. This is particularly important in high ambient temperature environments or when conductors are carrying high currents. In the provided scenario, the initial tests were done in winter, and the question arises whether extreme hot summer temperatures will affect voltage drop. The answer is yes. Higher temperatures will increase resistance and voltage drop. The temperature coefficient of resistance is a factor that quantifies how much the resistance changes per degree Celsius or Fahrenheit. This factor can be used to adjust resistance values for different temperatures and voltage drop calculations. Now let's discuss how to calculate voltage drop. The basic formula for voltage drop is volts drop equals current times resistance, often written as volts drop equals I times R. For alternating current or AC circuits, impedance or Z is often used instead of resistance or R to account for inductance and capacitance. However, for relatively short lengths of cable, resistance is often the dominant factor. For a three-phase system, the voltage drop calculation is slightly different than for a single-phase system. The line-to-neutral voltage drop is calculated as volts drop equals square root of 3 times current times resistance. The square root of 3 factor accounts for the phase relationship in a three-phase system. To perform the voltage drop calculation, firstly determine the conductor resistance. Look up the resistance per unit length of the conductor in standard electrical tables, taking into account the conductor material, size, and temperature. Secondly, determine the conductor length. Measure the length of the conductor from the source to the load. Thirdly, determine the current. Estimate or measure the current flowing through the conductor under normal operating conditions. Fourthly, apply the voltage drop formula. Use the appropriate formula for single-phase or three-phase systems to calculate the voltage drop. Fifthly, compare the calculated voltage drop to acceptable limits. National Electrical Code or NEC provides guidelines for acceptable voltage drop. A common recommendation is that voltage drop should not exceed 5% from the source to the furthest point of utilization. Now let's address the specific concerns raised in the question. The initial voltage reading of 455 volts phase-to-phase compared to the expected 480 volts raised concerns about excessive voltage drop. However, the second meter reading of 479 volts phase-to-phase indicates that the voltage drop is within acceptable limits. The discrepancy between the two meter readings highlights the importance of using accurate and calibrated meters. Meter accuracy is specified as a percentage of the reading, meaning that the error can be larger at higher voltage levels. Even small deviations in meter accuracy can lead to significant differences in readings, especially in high voltage systems. When troubleshooting voltage drop issues, it is important to use a calibrated meter and to take multiple readings at different points in the circuit. If the voltage is within acceptable limits under normal operating conditions, the next step is to consider the impact of increased load and temperature. As the load increases, the current flowing through the conductors will also increase, leading to higher voltage drop. It is important to calculate the voltage drop under full load conditions to ensure that the voltage remains within acceptable limits. If the calculated voltage drop exceeds the acceptable limits, there are several options for reducing voltage drop. Firstly, increase the conductor size. Using a larger conductor will reduce the resistance and therefore the voltage drop. Secondly, reduce the conductor length. If possible, shorten the distance between the source and the load. Thirdly, use a conductor material with lower resistance. Copper has lower resistance than aluminum for the same size conductor. Fourthly, increase the supply voltage. Increasing the supply voltage will reduce the percentage voltage drop. However, this may not be possible or practical in all cases. In addition to load, temperature can also affect voltage drop. As mentioned earlier, higher temperatures increase the resistance of the conductor, leading to higher voltage drop. In hot summer conditions, the voltage drop may be significantly higher than in winter. It is important to consider the maximum ambient temperature when calculating voltage drop and to size the conductors accordingly. If the voltage drop is excessive due to high temperature, there are several options for mitigating the problem. Firstly, use conductors with higher temperature ratings. Some conductors are designed to operate at higher temperatures without significant degradation. Secondly, provide adequate ventilation for the conductors. This will help to dissipate heat and keep the conductor temperature down. Thirdly, reduce the load on the circuit. This will reduce the current flowing through the conductors and therefore the voltage drop. Now let's discuss the potential long-term problems associated with excessive voltage drop. If the voltage drop is significant, it can affect the operation of equipment connected to the circuit. Motors may not start properly, lights may be dim, and electronic equipment may malfunction. In addition, excessive voltage drop can lead to overheating of conductors and equipment, which can increase the risk of fire. Long-term, excessive voltage drop can reduce the lifespan of equipment and increase maintenance costs. In a scenario provided, the 45 kV amps transformer is supplying a COM room. The equipment in the COM room is likely to be sensitive to voltage variations. If the voltage drop is excessive, it could affect the performance and reliability of the COM room equipment. It is important to ensure that the voltage supplied to the COM room is within the specified tolerances of the equipment. If necessary, a voltage regulator can be installed to maintain a constant voltage. Finally, let's address the question of whether added resistance to the transformer will be a long-term problem. The transformer itself has impedance, which contributes to voltage drop. If the transformer impedance increases over time due to degradation or other factors, the voltage drop will also increase. It is important to monitor the transformer performance and to replace it if necessary. In addition, loose connections and corroded contacts can also add resistance to the circuit, leading to increased voltage drop. It is important to regularly inspect and maintain the electrical system to identify and correct any potential problems. In conclusion, voltage drop is an important consideration in electrical system design and operation. Accurate calculations, proper conductor sizing, and regular maintenance are essential for ensuring that equipment receives voltage within its operational tolerances and for preventing long-term problems. By understanding the factors that influence voltage drop and by taking appropriate measures to mitigate it, you can ensure the safe and reliable operation of electrical systems. Remember to always consult with qualified electrical professionals for specific design and installation advice. This information is for educational purposes only and should not be considered a substitute for professional engineering guidance. Always adhere to the National Electrical Code and local regulations when working with electrical systems. The impact of voltage drop can extend beyond simple operational issues, potentially affecting the lifespan and efficiency of connected equipment. Understanding the nuances of voltage drop and its mitigation strategies is paramount for ensuring a robust and reliable electrical system. Let's explore some additional aspects related to voltage drop. Consider the impact of harmonics. Nonlinear loads, such as electronic devices, can introduce harmonic currents into the electrical system. Harmonic currents can increase voltage drop, especially at higher frequencies. Using harmonic filters can reduce harmonic currents and mitigate voltage drop. Another point is power factor correction. Low power factor can increase current flow and therefore voltage drop. Improving the power factor can reduce current and voltage drop. Power factor correction capacitors are often used to improve power factor. Also consider voltage drop under motor starting conditions. Starting a motor can draw a large inrush current, which can cause a significant voltage drop. This voltage drop can affect the starting torque of the motor and the operation of other equipment connected to the circuit. Using reduced voltage starters can limit the inrush current and reduce voltage drop during motor starting. And there are long cable runs. For very long cable runs, voltage drop can be a significant issue. In these cases, it may be necessary to use higher voltage distribution or to install voltage regulators at the load end of the cable. Furthermore, consider the impact of unbalanced loads. Unbalanced loads in a three-phase system can cause voltage imbalances, which can lead to increased voltage drop and equipment malfunction. Balancing the loads can reduce voltage imbalances and improve system performance. Let's talk about grounding and bonding. Proper grounding and bonding are essential for electrical safety and can also affect voltage drop. A low impedance ground path can reduce voltage drop during fault conditions and improve the operation of protective devices. Remember surge protection. Voltage surges can cause temporary voltage drops, which can affect sensitive electronic equipment. Surge protection devices can protect equipment from voltage surges and prevent voltage drops. Always think about maintenance and inspection. Regular maintenance and inspection can identify and correct potential voltage drop problems. Inspecting connections, tightening loose terminals, and replacing corroded conductors can improve system performance and reduce voltage drop. There are also software tools for voltage drop calculation. Several software tools are available for calculating voltage drop. These tools can simplify the calculations and provide more accurate results. And finally, the importance of documentation. Accurate documentation of the electrical system, including conductor sizes, lengths, and load information, is essential for troubleshooting voltage drop problems. The information provided here offers a comprehensive overview of voltage drop, covering its calculation, contributing factors, and mitigation strategies. By implementing these best practices and staying informed about the latest technologies, you can ensure the optimal performance and longevity of electrical systems.